Hello and welcome to College Physics 2, Lecture 2, Charge, Charging, and Atoms. To begin this lecture, we're just going to recap the two different types of materials we encountered in our previous lecture, that being conductors and insulators. These two different types of materials differ in the ability to move charge. On one hand, we have conductors, like metals, that allow charge to easily move through or along their surfaces. So there's a reason why a lot of our electronics, for example, use, say, copper wiring. Copper is a metal which is a conductor, and charges can easily flow through them. On the other hand, we have insulators, which are basically the opposite. Insulators are materials where charges are immobile. In other words, charges are not able to flow through them. Great examples of these would be plastics, rubber, wool, glass, and so on. Now, there is a technicality associated with these, and that's the fact that they can both have charges on them. They can both be charged. They just differ in how they move the charge. Again, conductors let charges move through them, insulators do not. So moving forward, we want to take a look at a few interesting situations. First is what happens when you put charge onto an object. In the example we've provided in the image on the right, you see a charged rod. Notice the negative signs, so that's indicating a negative charge on the rod, being tapped to this metal sphere. The charges, when tapped, will enter the sphere, but then there is a very interesting kind of situation where no matter what the shape is, how many charges there are, whether it's positive or negative, these charges will distribute themselves so that they reduce the overall repulsive forces between them, right? Because they're all negative charges, they want to move away from one another. They want to get as far apart from one another as possible. And so once they're in the sphere, they distribute themselves as quickly as possible to the external to the edges of this object, so right to the surface. And that's what the third image here is showing you. You're seeing the negative charges distributing along the surface of the sphere, and because it's a symmetrical object, in this case, they are evenly distributed around that sphere. So this happens incredibly quickly. You should just think about, flipping a light switch. The instant you flip that light switch, the lights come on. Charges move quickly. And so this process is very rapid as well. Basically, fractions of a second. Once the charges have distributed themselves in their most ideal way, like you see on the right, they don't move anymore unless there's something nearby to influence them. And so once they are in their positions, they're at rest where they want to be, we call that situation electrostatic equilibrium. I abbreviate that ESE just because I get annoyed having to write electrostatic equilibrium over and over again. Think about what that name means. Electro is indicating charge, static means not moving. So this is a situation where charges in a conductor do not move. Now, let's take this and learn about kind of a really, I think, fascinating result of some of this. And what we're going to look at is what happens when you have a neutral object, but one that can kind of in a way have a charge. So if you take a neutrally charged object like the sphere you see in the image at the top, and say you bring a positive rod nearby, well, think about what's happening inside of that neutral conductor, the sphere. Remember, even though it's neutral, it still has charges inside of it. It just happens to have equal amounts of positives and negatives. So once that positive rod comes close, the negatives, the opposite charges, are going to be attracted to that positive rod. And the like charges, the positives, are going to be repelled away from the positive rod. So we aren't adding or subtracting either type of charge here, we're simply separating them. Negatives toward the rod, positives away, like you see on the right. This particular separation of charges is known as charge polarization. It is polarized. You've heard of this term before. Think of just the word poles. That indicates a duality. Two, we have like a north magnetic pole on Earth, a south magnetic pole on Earth. we call those poles. Anyways, I'm digressing again. The point is, we are seeing charge polarization take place. It's still overall neutral. But because of this, we now see one more interesting thing happen. Notice that the negative charges are closer to the rod. The positive charges are further from the rod. We know that opposites attract and likes repel. But the opposite charges that are trying to attract are closer, and so the force is going to be stronger. So as a result, if this conducting sphere was lightweight and free to move, it could actually start moving toward the rod. It becomes attracted to it in what we call the polarization force. So here we're seeing a neutral object being attracted to a charged object. So it's kind of weird to think about that, right? A neutral object being attracted, but it can happen in this process of polarization. Before we move on in the lecture, I just wanted to add in kind of a cool discussion so that if you're like someone who's taking notes or something, this isn't something that's a part of my actual notes, it's just one of my asides. Well, it turns out that, believe it or not, bees actually have a great deal of, interaction with charge. And it matters, too, in the world. So when there is a fair weather day, so, not a lot of storms nearby, generally speaking, the air is positively charged. And a bee flying through the air is going to bump into charged particles, and basically the friction of them bumping into those charges is going to strip away electrons from their surface. And so they end up with positive charges as well. On the other hand, flowers, because of the positively charged air, tend to have a negative charge. So, oops, I just made a mark there. That was an accident. But let's take a look at this. So I'm going to very poorly make a sketch. Let's say this is the Earth's surface, and you have a flower sitting up here. This is a very large flower compared to the Earth. I'm not an artist, by the way, so bear with me on this. So we're saying that the air is positively charged, right? So there's all these positive charges up here. Well, we know that opposites attract, right? So the Earth, which has a significant mass of positive and negative charges, they're all over the place in here, but the negative charges are going to be attracted up toward the positively charged air. And so the flower is going to end up with a net negative charge. So when a bee lands on a flower or goes near the flower, it is positively charged. The flower is negatively charged, which means the pollen that's also on the flower is negatively charged. So the positive bee comes in, the negative charges in those little particulates of pollen are going to attract to the bee, and it's going to stick to them. This is actually a photo that I took very close to where I live in central Oklahoma of a bee on a thistle, and you can see this guy's living it up. He's got pollen completely coating his entire body. So that's very likely an electrostatic attraction for this very reason. Now this has actual implications in the world because pollen is basically how flowers spread their seed and can grow elsewhere, and so this bee is acting as a pollinator now. He can, wherever he flies and lands next, some of that pollen's going to fall off of him or attach to whatever he lands on, and so on and so forth. So it's just kind of a really cool real-world example of these charges influencing things in the world. All right. At this point, I would ask that you pause this video and watch the video that I linked here. This is a link that you'll find in the description of this video as well. There's no audio or no a verbal instruction or description of what's happening, but the video makes use of plus and minus signs on the screen to help you visualize what's occurring in this demonstration of what we call a Franklin's bell. I encourage you to watch it, honestly, probably twice, once to just get an idea of what they're doing, and then again to better understand what's happening. I'm being vague because you'll watch the video, hopefully, but I very strongly encourage you to. I think it's fascinating. Okay, so let's learn a little bit about ways we can charge objects. In our first lecture, we saw the frictional process of charging where we rub objects together. In this case, we're going to learn about conduction and induction, two ways to charge objects. Let's start with the simple case of conduction. Conduction is a process that occurs whenever you have two objects that physically come into contact with one another. Or perhaps they're connected by a conductor, so a wire connecting between them perhaps. In the process of conduction, the total charge of the two objects is equally shared between the two bodies. So as an example, I have an image here on the right. You can see object A has a charge of positive 12. Object B has a charge of 0. So in this process of conduction, let's touch them together. Their total charge, which is 12 plus 0, is then equally shared between the two. They split that charge. So you split it up. 12 divided by 2 is 6, so they each get 6 charge as a result. This is a way you can charge objects, right? This is the process of conduction. So now object B, which was originally neutral, now has a charge of positive 6 as well. So they shared their charge by physically touching each other in the process of conduction. But that's not the only way you can charge things. Induction, on the other hand, gives the object the opposite charge, right? So in conduction, we saw them both getting positive charges. But with induction, you can give an object the opposite charge of whatever you have initially. So let's go through a scenario here to show this process. Start with two neutral spheres touching each other, like you see in situation A on the right. Let's again bring a positively charged object nearby, but this time we're not going to touch it to the spheres. We're just going to bring it close by. In this case, we see the effect of polarization again. In situation B, you can see the negative charges of the spheres are going to be attracted toward the positive charges of the rod. Alternatively, the positive charges in the spheres are going to be repelled away from the similar charged rod. So what this means is the negative charges are accumulating in the sphere on the left, the positive charges are accumulating in the sphere on the right. If you separate those two spheres, well then there's nowhere for them to go anymore. The negatives are stuck on the one on the left, the positives are stuck to the one on the right, and then once you take the rod away, it doesn't matter. They're separated now, and so the charges are stuck inside of their individual spheres. So this is a way you can charge things known as induction. They end up with opposite charges. Now this said, there's actually a second way you can charge something with induction. So let's go through another scenario. This time with a single sphere and a positive rod. If you bring the single sphere close to that positively charged rod, we'll again see polarization. Negatives pulled to the left, positives pushed away to the right. Now, connect a grounding cable to that sphere. That is, a cable that connects into the earth. If you don't know what I'm talking about, just in any household in the United States, we have 3 holes in our outlet. There's the 2 on top and then the 1 hole on the bottom. That's your grounding hole. That's where, if you have a 3-pronged cable, that bottom prong is the ground cable. So if you connect a grounding cable to the sphere, that allows a path for charges to flow from the sphere to the earth, or vice versa. So what's actually happening is negative charges from the earth can come in and basically cancel out the positives that are left up there. And then you remove that cable, the only thing that's left behind are the negatives, and thus you have a negatively charged sphere as a result. Now, it's kind of hard for people to think about negative charges flowing up into the sphere out of the earth, even though that is physically what happens. So another way to just think about it conceptually is you can just think about like the positives here, pushing the positives away in the sphere, and once they have an escape route, they take that, right? They want to get away from the positive rod, so they escape the sphere down into the earth. That's a fair way to look at it if it's easier to think of it that way. But just know that it really is negative charges moving up into the sphere. We'll talk about why that is the case in just a moment. Because now we're going to take a closer, literally, look at this by going down to the atomic level. So a few minor notes of chemistry here. This is some basic chemistry material that we've probably all seen before, I hope. We should have a basic idea of what an atom looks like, right? An atom has a nucleus, a dense nucleus at the center. It's positively charged because it contains protons and neutrons. Protons have a positive charge and neutrons have a neutral charge. But overall, because of those protons, it's a positive nucleus. That nucleus is then surrounded by the much less massive, negatively charged electrons. And these can, quote-unquote, orbit at great distances away from the nucleus. But they don't really orbit like planets around a sun, as we've learned because of modern physics and everything like that. It's more like an electron cloud. We don't really ever know exactly where one electron is, but we know based on probability where it should be. This is, again, digressing, getting a little bit ahead of myself. But the point is, you have the positively dense nucleus, the negatively charged electron cloud around that. Now, these electrons and protons are the sources of charge in the universe. There are no other sources of charge anywhere. So we consider these to be the fundamental charges. So, whenever something is charged, remember, we're not saying it only has positives or only has negatives inside of it. It just means that there's an imbalance. It has more of one than the other. And this makes sense when you think about the atomic view. I mean, you can't ever just only have these protons floating around or only just have the electrons floating around in an object. And so it's just an imbalance. So most large, or what we call macroscopic objects, will end up with a roughly equal number of both. So you as a human, the Earth, larger objects like this, even if there's a few more positives than negatives, or vice, even if there's a few in terms of imbalance, there's just so many there that it's still basically neutral. And so we say that that object has no net charge and it is electrically neutral. So the way you actually get charges to transfer is by adding or removing electrons. So whenever we have a positive charge, the object didn't become positively charged because it gained those positives. It becomes positively charged because it loses its negative electrons. And this makes sense when you think about it at an atomic scale. The protons are tightly bound to the nucleus of an atom, but the electrons are kind of freely floating and sometimes often loosely out in the outer regions of the atom. And so it's the electrons that can be removed from your atom and shared. So we're either talking about gaining electrons, thus gaining a negative charge, or losing those negative electrons and becoming positively charged. The process of moving these electrons around is called ionization. And I just threw in some definitions at the bottom. They're not super relevant, but if you ever hear the term ion, this will give you an idea of what we're talking about. Anytime an atom is missing an electron, it becomes what we call a positive ion. And if it gains an extra electron, it's considered a negative ion. Now, we're getting ready to build our first equation in the course, which won't show itself until our next lecture, but we can at least build the framework here. Charge, from here on forward, is represented by the symbol Q. Now, for single charges, we use lowercase q. Later on, we will see capitalized Q as well. That tends to indicate the total charge on an object, but again, that's for future reference, but there's still both the letter Q for charge. The SI, or metric unit that we use of charge, is known as the coulomb, which is represented by the capital letter C. Now again, protons and electrons are what we call the fundamental charge. They are the source of charge in the universe. And they have the same amount of charge, protons being positive, electrons being negative, but their value is the same. We represent this fundamental charge with the letter E, and it has a known value of 1.6 times 10 to the minus 19 coulombs. That is a value you will use likely quite often in problems throughout the semester. So keep that number in mind. If you are in my class, it's on a formula sheet that I provide, so you don't have to memorize it, but you probably will anyway since you'll be using it often. Now, just thinking about this, that charge is associated with electrons and protons, right? So this explains why charge is conserved, right? Because electrons and protons aren't created or destroyed, so neither is their associated charge as well. So that is why in the last lecture, we made the statement that charge is conserved. It is known as a law in physics. So this has implications now. We talked about two different types of objects at the start of this lecture, conductors and insulators, and now we're kind of just getting a vague idea on why there is that difference in the first place. In an insulator, where charges don't really move, the electrons are tightly bound in the atom. So they're not really free to move around, and so charges aren't moving. And so as a result, we don't see a charge able to flow through the object, and thus we consider it an insulator. On the other hand, in conductors like metals, the outer electrons, which we call valence electrons, are weakly bound to the nucleus of those atoms. And so as a result, as these atoms come together to form the metal, the electrons can kind of flow around in what we consider a sea of electrons. They're free to just kind of wander around. And so that's why we see charges flowing through metals, because of their weakly bound electrons in the atoms. We could spend a lot longer going through this, but this is just your very basic view of why we have a difference between these two materials. This brings us to our last topic for this lecture, and that is electric dipoles, another topic we will come back to down the road in more detail. If you were to bring, say, a positive charge near an atom, a single atom with its positive nucleus and negative electron cloud, you can actually polarize the atom itself. If you think about this, because you have basically two separate distinct units, the negatives and then the positives in the nucleus. So bringing a positive charge nearby is actually going to tug on the negative electron cloud and try to pull it toward the positive charge. But that positive nucleus of the atom wants to be repelled away from the positive charge, so it pushes off to the other side. And so what you end up with is a slight imbalance, where there's more negatives on one side of the atom, more positives on the right side, and so we see an electric dipole. This is a polarization effect, and just like we learned about earlier, because of this, you will see a force generated, an attractive force. So the atom is actually going to want to be attracted toward that positive charge because the negatives are closer and opposites attract. Now, we're talking about a single atom, of course, so this force is incredibly small and basically irrelevant. However, real objects in the world are made up of tons and tons and tons of atoms. So if this effect is applied across every atom in that material, then it can have a noticeable effect. And we will see that soon. To conclude this lecture, let's just do a couple questions. So if you haven't seen any of these questions that I do before, the way I do this is I'll put the question up, I'll read it to you, and then I'll just let you pause the video so you can sit and think about your answer before I give my answer. So as soon as I'm done reading it, pause the video so I don't say the answer right away to you, because you should genuinely try to answer these yourself first. So question number 1. Consider two objects, A and B. Object A has a net charge. Object B is uncharged. Based on this information, which of the following is true? Take a moment to think about it, and let's answer it. This is an interesting problem, and it's the very first one I give in Physics 2, and everyone loves it. It's actually a trick question, because there really isn't enough information to tell. The answer is E. Keep in mind that both conductors and insulators can be charged. The difference is the ability to move that charge. So, sure, one has a charge and one is uncharged, but it doesn't give us any information about whether that charge is moving through it or not. So we genuinely don't know which one's the conductor or the insulator, or it could be both a conductor, both an insulator. We don't know. There's not enough information. Okay. Question 2. There's a picture associated with this. Metal spheres 1 and 2 are touching. Both are initially neutral. There's 3 steps to this. First, the charged rod is brought nearby. Then it is removed. Then the spheres are separated. So what would the charges be on the spheres after all of that? All right. Well, this is interesting. So you bring the charge nearby. The first thing that's going to happen in those spheres is they're going to polarize, right? You're going to get your negatives. Let's see if I can get my drawing going. So you're going to have negatives attracted to one side. Oh, what happened? There we go. And you're going to have your positives repelled off to the other side. But then you take away that influence. You're taking away the charged rod as soon as you bring it nearby. And so those charges go back to where they were. Then you separate the spheres. Well, there's no positive rod nearby to cause an influence anymore. So they're just back the way they were. The answer here is E. They are both neutral still, both a charge of 0. Now, question 3. It looks similar, but I did change it. Same setup, we're just changing up the steps. This time, bring the charged rod nearby again, then separate the spheres, and then remove that charged rod influence. What would happen in this case? Okay. Well, again, we will see, once that charged rod is nearby, polarization take place. You're going to see the negatives accumulate toward the positive rod, the positives repelled away from it, and now the next step is to separate the spheres. So basically, just imagine taking sphere 2 and moving it over. The negatives are still stuck in 1, the positives are still stuck in 2. Now it doesn't matter what you do with the rod, if you remove it or not, they're changed. The first sphere, Q1, is going to be negative. Q2 is going to be positive. So the answer is C. All right. This concludes Lecture 2. We will now move into a briefer Lecture 3, where we introduce Coulomb's law, which is an equation, and then just work out some examples using that equation. The very first one of Physics 2. As always, thanks for watching, and have a great day.